Okay, so good morning. Happy New Year to everybody. If you had a good holiday. It feels to me always, well, particularly this year, 3rd of January, 8 o'clock in the morning feels like a very sudden, a very rude awakening in the new year. But anyway, to mitigate for that, I've decided to make the lecture a little bit gentler today than, for example, the last lecture, which was really quite technical. The other thing to say is that more or less everything that could go wrong did go wrong this morning for me. So at home, our printer was out of ink. So I came to the department to print out my lecture notes, and at the department, I couldn't get a connection to the printer for some reason. I don't know, that it wasn't here early enough to get it sorted out in advance. So I haven't been able to print out my lecture notes. On the other hand, I wrote them not very long ago, and I've just jotted down the headlines here, so I think I can improvise, but I may at some point have to go to the computer and refer to the lecture notes, hopefully not. And the other thing is, the other essential for me of an early morning lecture is a cup of coffee, and I got to the machine this morning, and the machine is out of order. So anyway, nevertheless, we shall hopefully survive. So what do I need to do? This I think is working okay on Zoom. Right. So okay. So today, well, just to say, as I sent an email announcement yesterday, today's lecture is going to be in 2 parts. So today we have roughly, but it's really going to be approximate, and we'll see how much time we need for the second bit. So roughly 2 hours of lecture. And then the last hour is essentially a consultation period in case you have any questions about the homework. So consultation. Homework. But if the lecture part overruns slightly, that's okay. But nonetheless, even if we're not spending the full last hour on the consultation, there will be a period of consultation at the end. So basically, for you to ask questions and hopefully for me to help without giving away the answers, so to speak, but still offer helpful advice. Right, so let's start on the lecture material. So today what we're going to cover is a new side of complexity theory. And so today we're in lecture 12, and the lecture is going to be on the complexity of counting problems. This is a topic that there are some very beautiful but also very technical results. And for today's lecture, I'm going to state one of the very technical results at the end. So we're going to understand the statement of one of the main theorems in the area, but the proof is really a substantial piece of work, so we're not going to cover the proof of that. I am, however, going to do one little technical proof in the middle, not something very difficult, but still a nice little result that illustrates some of the issues that arise in counting. So, to say what I'm talking about with counting problems, well, actually, we've seen a few counting problems arise already in the student presentations, so I should refer to those when we come to that. So we have essentially encountered counting problems already, but we haven't treated them systematically yet in the course. And what I want to begin with is making a distinction between the kind of complexity we've been looking at and the kind of complexity we need to do if we're going to study counting problems. And that's based on somehow a dichotomy in the kind of computational problem you might consider. So there are essentially two kinds, well, there are many kinds of computational problem, but one might separate out or highlight two main classes. One is the class of decision problems, which is what we've been considering so far. So far, this course has focused on decision problems and their complexity classes. We can view a decision problem in three equivalent ways. Two of them, the main ones we've been looking at. So we can view decision problem three ways. So the first one is the main idea that gives rise to the notion of a decision problem, a problem which we give to a Turing machine, and the Turing machine decides what the answer is. So it says either accept or reject. So we give the Turing machine some word over an alphabet sigma, and we either accept or reject the word. But the second way of looking at decision problem, and as I said, they're equivalent, and we've been basing the whole course on this equivalence. The second way is to look at a decision problem as asking the question, does a word belong to a language? So we view the decision problem as a language, namely a set of words. So membership in a language. So the language is a set of words over the alphabet. And the third way, which we've not particularly been focused on, but it's trivially equivalent to the first way, is to consider a decision problem as computing a function that, when given an input, gives us one bit of output, either 0 or 1, so where 0 means reject or 1 means accept. So a function, so the third equivalent way is functions from or rather a language will correspond to a particular function. So computing a function from sigma star from our input alphabet to 1-bit answers. The decision problems are a special case of computing functions, but they're obviously quite a limited case of computing functions. And very many natural computational problems, a lot of what one does in computation involves computing functions where you want more interesting answers than 0 or 1, than just a 1-bit answer. So it is natural to extend complexity classes or rather, not really extend, but consider complexity classes that cater for. So whereas the complexity classes we've been looking at so far are all classes of languages, so all classes of decision problems, because we're often interested in computing functions, it's natural to have classes of functions and to group them together according to how difficult it is to compute functions. So it's natural to adapt complexity beyond decision problems, languages. So complexity classes consist of collections of functions. So in general, you might even allow functions from strings over one alphabet to functions of strings over another alphabet. So the idea is to go beyond decision problems. And we're going to do that immediately by making a definition, which is not really new content because we've been working with it implicitly already in the course. We just haven't given a word to the complexity class, or rather than a word, an acronym to the complexity class. So we're going to look at, so in a sense, with the complexity classes for decision problems, everything was built up over the basic class, which was almost the smallest class we considered, of P, of polynomial time decidable problems. Wasn't quite the smallest class because we also considered logarithmic space and non-deterministic logarithmic space. But in any case, the most basic class was the polynomial time decidable languages. And we're going to have an analogous class of functions now, which is the polynomial time computable functions. And we've already been working with such functions, for example, to do our reductions from one language to another. We've been using such functions, but now we're going to collect them all into a complexity class. So this complexity class is the class that we think of as the class of efficiently computable functions. So the complexity class FD so this is the class of functions from one language, from one alphabet potentially to another. For which the definition is exactly what we would expect. We want to say the function is computed by a deterministic Turing machine that runs in time polynomial in its input. So we say for which there exists a deterministic Turing machine M that computes F. And what computes F means is defined in lecture 2. But it's the obvious thing. You run the Turing machine on an input word, the Turing machine must necessarily hold, we require that it holds, and when it holds, then we consider it as giving an output, which is the word left on the tape at the end of the computation, and we require for an input word W that the output left on the tape at the end of the computation is the word F. So there is a deterministic Turing machine that computes F, and there exists a polynomial bound to the running time. A polynomial D and N such that for all for all possible input strings, so for all W, the input alphabet, time of the Turing machine, capital M, on input string W is less than or equal to E of the length of W. So the running time is polynomially bounded in the length of the input. Okay, so very natural definition, and we've already been working with it informally, as I've said. So we've been talking about polynomial time reductions from one language to another. When we said that, we really mean the reduction is in the complexity class FP, and the definition is completely as we expect. Now, I know I can put the board up, but I think I want to keep this part down, so I'm going to erase this and then put it up a little bit later. So let's make some observations about the complexity class FP. Observations. So firstly, if f belongs to fp, so if it's a function that's polynomially computable. By the way, I should have said fp stands for function polytime. Polytime is, of course, short for polynomial time. So if we have a function that's fp, of course it cannot, the function cannot expand its string, input string, too much to get the result. You've got a polynomial running time in the length of the input string, so the output string, the length of the output string must be polynomially bounded in the length of the input string. So I can state that more formally. It's stated more formally in the lecture notes, but I think you know what I mean. So the length. So if f is in, should start with if f belongs to fp, so it's in function polytime, then the length of fw, so the length of the output string, is polynomially bounded. In the length of W. Secondly, we've been talking about functions from one language, from one alphabet to another alphabet. There's a particular case, special case, that's going to be particularly important, and that's, so often when we compute numbers, we're computing numbers, often when we compute functions, we're computing functions on numbers. So the particular special case is what this definition means when we're thinking of a function as a function on numbers rather than a function on strings. So for example, so I'm going to consider the case that's going to be most relevant to us, which is going to be functions from strings to numbers. We say that a function from strings to numbers belongs to fp if the function that given input W computes binary representation of W is in FP as a function on strings. So that's a function. So that's a function from strings over the input, alphabet sigma to strings and binary bits. Okay. So the primary definition of FP is for functions on strings, but we just use we abuse terminology and talk about a function on a function to the natural numbers being in FP as well, in the natural way. In complexity theory, we're all used to by now, everything is coded as strings, and particularly numbers as binary strings. And similarly, for functions from n to n, so functions of the natural numbers, and then we say etc. So basically, whatever kind of function we have, we code it up using strings, and then it belongs to FP if and only if it belongs to FP according to the string transformation notion of FP. Okay, so let's consider some natural functions. They might not seem so mathematically natural functions, but they're this kind of functions that arise somehow, well, they've got a little bit of combinatorial flavor to them, and analogous functions arise in combinatorics. And as you'll see, they're very related to the sort of material we've been discussing on this course. So this takes us actually to the title of the lecture, which is counting problems. And counting problems are a natural source of computational problem from an alphabet to the numbers. So counting problems are an abundant source, let's say, there are plenty of them, of interesting computable functions from some input alphabet to the natural numbers. So what do I mean by counting problems? Well, first example is called sharp sat. So counting problems tend to be prefaced by the hash, which is called sharp, I guess, because it looks a bit like the sharp sign in music. Maybe it was originally actually the sharp sign in music in the original papers on this, I don't know. And now people tend to use the hash anyway. Anyway, people say sharp sat. So this is the counting problem associated with satisfiability. So this is a function from whose input alphabet, so it's words over the input alphabet, let me call it sigma prop, which is the input alphabet we use for coding propositional formulas. Alphabet propositional formulas. We've been looking at encoding. We've been working with encoded propositional formulas ever since the satisfiability problem. So the sharp sat problem is a function from propositional formulas. We said we read the strings of propositional formula and we return a number n. And what it does is it counts the number of satisfying assignments that for the formula. So sharp sat of formula phi is defined to be equal to the number satisfying assignments. Remember, a satisfying assignment is a function from the variables in the formula. This is a function of the variables, the propositional variables in phi 2, 0, 1, truth values. That makes the formula true. It's a satisfying assignment if the assignment of truth values to variables makes the formula true. That makes phi true. So the satisfiability problem itself was deciding, does there exist a satisfying assignment? And here we're doing something much stronger than that. We're not asking just does there exist one, but we're trying to count the number. But this function is counting the number of satisfying assignments. And this example is a prototype for many other similar definitions. So we can take any of the other problems we've been looking at. So, for example, free coloring problem. Make a sharp version of it. So sharp free col would take. So now we take the input alphabet is going to be the alphabet we use for representing graphs. We're going to map any string over that alphabet to n. And now we want to count the number of three colorings of a graph. So half free col of a graph G is the number of three colorings English spelling of G. There's always maybe a little bit of ambiguity in how this is defined, because you might say, are we counting the number of really fundamentally distinct three colorings? So if we permute a given three coloring by a permutation of the three colors, does that count as a different three coloring or not? So there are at least two different ways one might count this. Let's just, for the sake of simplicity, say we're simply counting the number of three colorings. That's the number of mappings from vertices to three colors that satisfy the three coloring property, no two adjacent vertices. But everything I say will also apply to the other counting problem too. Anyway, so we've got the sharp free col, and as you can imagine, for other decision problems we've considered that have the property that they're defined using some form of witness. Here, the witness, some form of certificate. The satisfiability, the certificate is a satisfying assignment. The three colorability, the certificate is a three coloring. For Hamiltonian cycles, the certificate is a Hamiltonian cycle of the graph. Whenever you've got a definition of a language in terms of the existence of the certificate, there's a corresponding counting problem which counts the number of certificates. So let's formalize that, because that actually gives us another important and interesting complexity class of functions. We have one complexity class of functions, which is the class FP, and the second one is going to be the class of functions we get by counting certificates for two NP problems. So recall the certificate definition. Okay. So L belongs to NP if and only there exists a Turing machine, there exists a Polytime Turing machine. And such that a word belongs to L if and only if there exists to be there's some alphabet of certificates, polynomially bounded in length W, such that N is WD. And the polynomial P. So we're familiar with this, that the language is in NP if and only we can reduce membership of the language to search for a certificate that proves that the word belongs to the language. And the certificate needs to have length polynomially bounded in the length of the word that we're trying to show is in the language. So whenever we have a formulation of an NP language in this form, so every NP language can be formulated in these terms. There may be several different and non-equivalent ways of formulating it. I mean, they'll be equivalent, they define the same language, but they might have very different forms of certificate for the same language. But whenever we have such a formulation, there is a corresponding counting problem. So, corresponding counting problem is function from input words in sigma star to N K. K of W is the number of certificates. So here I'm taking the cardinality of the set of certificates. So that's the number of certificates such that we should have said here MD. What this meant was that M with the input word and the certificate accepts. And here we have MWB accepts. Okay, so at this point I just need to reflect a little bit because I'm a little bit missing my notes, but so basically we want to define the complexity class sharp P as the class of all those functions that arise in this way. So sharp P is defined to be the class of all functions K as above that arise from M and P as above. So here the M and P are the data that is demonstrating that a particular language belongs to NP. Okay, so the language for any NP language, we have an M and we have a Turing machine M and a polynomial P, and such that that Turing machine decides whether a certificate proves that a word is in the language. And given that data N and P, we determine the counting function K associated with it, and that counting function is by definition a member of the class sharp P. So sharp P is those counting functions that arise as functions that count certificates for NP problems. Okay, So clearly, we know that SAT is an NP problem, and here we're counting the number of certificates. We know that 3 colorability is an NP problem, and here we're counting the number of certificates. So clearly, SAT, so sharp SAT, and sharp 3 col belong to sharp P. Okay, I still want to leave this up here, so let me go back to here. So if you've got a function belonging to sharp P, what can we say about the extent to which it can expand its input string? So suppose F belongs to sharp P. How long can the output string F of, so we apply F to an input word W, and so F is counting the number of certificates that W belongs to some NP language L. How long can that? How long is the binary representation of that number? Potentially. Can anyone see? So there are most. So the length of a certificate is polynomial in the length of W. We've got some finite alphabet sigma for our certificates. So we've got some finite exponent power whose exponent is polynomial in the size of W, but then the length of that will be logarithmic of that. So that's still going to be O of P of W. So the length is still going to be polynomially bounded in length of W. So this is answer polynomial length of W. So it's plausible from the point of view of length perspective. It's plausible that that sharp P computable functions might belong to FP. They might be computable in polynomial type. So does that sound very plausible? So let's say, so we can ask, does every sharp P problem belong to FP? As a remark, I'm not going to tell you the reason why now, but as a remark, you can think about this, how to work it out. So as a remark, every polynomial time computable function does belong to sharp P. So if you've got a polynomial time computable function, you can cook up some language, some NP language such that the polynomial time computable function counts the number of certificates of showing that a word is in the language. So FP is a subset of sharp P, but we're asking, does every sharp P problem belong to FP? So I wonder if it's nearly time for the break. I wonder if any of you have an intuition about this. So there's a kind of glaring reason for the answer to this. I mean, is it plausible that every sharp P problem belongs to FP? So sharp SAT, yes?
I think of FP as the analog of P, right?
So FP is the analog of P, yes, we can compute. Yeah, so the functions we can compute in polynomial time.
Yeah, the sharp P is more of an analog to NP.
Yes, it
That's
is.
what I think about.
So you're saying it's not very plausible?
Oh.
Because it's like it's a bit like the NP equals P question. So that's the right intuition. But I mean, more strongly than that, we can say, let's call this proposition. So we can ask, does every sharp P problem belong to FP? So is it polynomially time computable? But this is unlikely. And the reason it's unlikely is the following, that if sharp SAT belongs to FP, sharp P, sharp SAT of course belongs to sharp P if it belongs to FP, if it's polynomial time computable. So we can polynomial time compute the number of satisfying assignments, then P equals NP. And in the notes that I'll publish online, there's a little bit of a detailed argument for this, but it's actually basically obvious, because sharp SAT is computing the number of witnesses, the number of certificates, the number of satisfying assignments to a satisfiability problem. So if you can compute the number of satisfying assignments, then you can clearly polynomial. If you compute that in polynomial time, you can simply test if it's equal to 0 or not, and then you've solved the satisfiability problem in polynomial time. The only slight bit of care one needs is moving between the complexity classes F, P, and P here, but basically everything falls out from the definition. So sharp P is almost clearly a more difficult complexity class than FP. You're right, it is like an analog of NP for function problems, but it turns out to be a much more powerful class than NP. It's much harder to compute sharp P problems in general than it is to compute NP complete problems. And the reason for this is that somehow counting the number of solutions to something is in general harder than deciding, does there exist a solution? Now we haven't really seen that yet with, sharp satisfiability is a problem that it's hard to decide and it's hard to count the number of solutions to. Then what I want to begin the next part of the lecture with is a problem that is easy to decide, but nonetheless we can prove that it's hard to count the number of solutions to. Okay, so we'll have a 15-minute break now. I shall pause the recording. Find the right button. Okay, so I want to begin this part by we've seen that counting problems are in general hard in the sense that we certainly, if we can solve all sharp P problems in polynomial time, then P equals NP, which is unlikely. In particular, if we can solve the sharp SAT problem, counting the number of satisfying assignments to a propositional formula in polynomial time, then P equals NP. And that's not that surprising at all. What's more interesting is that there are some natural problems that it's quite, so with satisfiability, already deciding if there exists a satisfying assignment is hard. So now I want to consider an example of a problem where deciding whether there exists a solution is easy, but counting the number of solutions is hard. So a problem deciding the existence of a solution. It's easy. But counting the number of solutions appears hard. Appears to be hard. And this is the problem cycle, which decides if a directed graph has a cycle. Input a directed graph. Question, directed graph G. The question to answer is, does G have a cycle? So let's call it a directed cycle. Because by a cycle, I mean a cycle that follows the directions of the arrows in the directed graph. So I'll be careful as I say directed cycle. And it's not hard to see that this has a solution in polynomial time. So this is, I'll leave that as an exercise. I've probably done similar things in algorithms courses. This is decidable. Well, it's decidable in polynomial time. I just say it in the short way. Cycle belongs to the complexity class P. In fact, there's apparently a linear time solution to this. And the right way of formulating it, you can find a linear time solution. According to the textbook. So what I want to consider is a counting problem associated with this. So counting problem, hash cycle. Well, the obvious one to say would be so hash cycle of G, for the graph G, is the obvious one would be the number of directed cycles in G. Little issue with this, which is what do you mean by directed cycle? Because depending on your definition, so if you've got a directed graph and you've got, say, a loop from here to here, then one cycle, let's say S and T, one cycle goes from S to T and back again to S. But depending on your definition, I mean, the ordinary definition of a cycle, S to T to S to T to S would also be a cycle, as long as any path that goes back to the starting places under the basic definition of a cycle is a cycle. And so we can't count cycles in that sense, because as soon as there's one cycle, there are infinitely many sub-cycles. So the obvious thing we do is we ask for cycles that don't ever repeat. And these are called simple direction cycles. So simple means no vertex visited twice. But even having said this, there's an ambiguity in the problem as specified in what we're counting. So in this graph here, the simplest graph, well, we could even have a self-loop if we want, but it's a very simple graph with cycle. Do we count this as having one simple cycle or two simple cycles? So do we count the cycle that starts at S and comes back to S as a different cycle from the cycle that starts at T and comes back to T? So it's a question on how we want to make the definition. And actually, for what I'm going to say, it doesn't matter which definition we take. So what will follow is independent of this. Well, anyway, let me just tell you what will follow is independent of this. But for definiteness, I'm going to say we count a cycle. A cycle is a sequence of vertices starting at some given initial vertex that never repeats, but the last vertex has an edge back to the first vertex. And so under that definition, this graph has two cycles rather than one cycle. So here, a cycle is a sequence of vertices that repeats. Simple. Sorry, I should say a simple cycle. Sequence of vertices that never repeats. So and whose last edge connects to and whose last vertex connects to the start vertex. But I won't write it down, but just to say everything I'm going to say would also work, and you can check that for yourself, if we said that actually we count the number of such cycles up to cyclic permutations. So modulo, so for every difference in this graph is on this one side. Right, so what I want to show you is that, so clearly it's not hard to see that hash cycle belongs to a sharp P. So not hard to see that sharp cycle belongs to sharp P. So it is a counting problem of the form we're considering. Is that it is inherently hard to compute. Of course, it's always pretty much impossible to show absolutely that things are hard to compute. So, show it's hard to compute. We're going to have a proposition, and it's in the standard form. If we could compute it in polynomial time, then something we don't believe is true. And can anyone guess what that thing's going to be? So if sharp P belongs to FP, so what we want to show is we don't believe we can compute the, sorry, not sharp P, sharp cycle. We don't believe we can compute the number of cycles. If sharp cycle, we don't believe we can compute that in polynomial time, then guess what's going to follow?
FP is equal to short p.
Good guess, but no. We don't know that. Or at least I don't know that. But something, a more standard thing that we don't know. P equals FP. And this is, it's a reduction, but it's a nice little reduction. So this is the technical bit of the lecture. We're going to do this argument. So we want to prove this. So what we're going to do is, well, we suppose we've got a polynomial time. I suppose we have a p-time algorithm for counting the number of cycles. Or number of cycles. What we're going to do is we're going to show that we can solve an NP-complete problem in deterministic polynomial time. So we show that we can solve the NP-complete problem called DHAM in polynomial time. So DHAM is input a directed graph and question, does the directed graph have a directed Hamiltonian cycle? Directed graph G, question, does G have a directed Hamiltonian cycle? So a cycle that visits every vertex of the graph exactly once. Okay, and I don't actually remember if in the exercise classes Hamiltonian cyclicity, the existence of a Hamiltonian cycle for a directed graph was one of the exercises considered. Probably it was at least considered for an undirected graph as one of the NP-complete problems. Anyway, it's one of the classic NP-complete problems, and we're going to solve that in polynomial time, given our supposed polynomial time algorithm for counting the number of cycles. Okay, so we're going to give a polynomial time algorithm that's going to use our algorithm for counting the number of cycles in a directed graph. We're going to use that to solve the Hamiltonian cycle problem. So our algorithm or DHAM works as follows. Okay, so we're going to input a directed graph G. So accept the directed graph G as input. And we want to decide whether or not it has a Hamiltonian cycle. So to do that, we're going to transform G into a bigger graph such that the original graph has a Hamiltonian cycle if and only if in the bigger graph the number of cycles explodes. So we're going to be able to look at the number of cycles in the bigger graph and from that determine if it's a very, very large number. It can be a very large number only if the original graph had a Hamiltonian cycle. So we construct a new graph G prime from G as follows. And this is the graph to which we're going to count the number, in which we're going to count the number of cycles from G as follows. I got this argument in the textbook, I think it's quite a nice argument. So we replace every edge in G with a gadget, which is a graph of replacing that edge. So we're expanding the graph by inserting collections of nodes wherever there was an edge in G. So we replace every edge U to B in G with the following in G prime. What we want to do is we want to force in G prime there to be a large number of paths from U to B. So we put U here and V here, and we're going to make a large number of paths between them by having a number of steps. Or at each step, you can make two choices to get to the next step, and so on. So we can this picture. Oops, these are a bit distant. Closer. Where the depth here, the number of nodes here, we're going to call this n. The number of nodes, the distance along here. And this is going to be n ceiling of log to the base 2 of a. Okay, I hope. I'm beginning to wonder if I'm actually remembering my notes correctly, but I think this is right. So here, so where G has n nodes. So the n is the number of nodes in individual G, and here for every edge, we're adding for every edge in G, we're adding 2n new nodes to G prime, and I don't know, 4 times n plus 4 new edges, or we're taking one away, so 4 times n minus plus 3n new edges, or something like that. Anyway, so in G prime, how many paths are there from U to B? Directed paths. So how many different ways are there of getting from U to B?
2 to the power of
Right, 2 to the power of n. So and this is for each edge in G. And also, because this is acyclic, this little bit that we put in this picture above, this little bit here, the new G prime we have, all its cycles will come from G. Although there are going to be numerous cycles for each cycle from G, because depending on how many ways we go along the paths, but still each cycle in G prime comes from an underlying cycle in G. So let's see, if G has a Hamiltonian cycle, we want to ultimately decide if G has a Hamiltonian cycle. what I want to do is show that if G has a Hamiltonian cycle, then we have some large number of cycles in G prime. And if G doesn't have a Hamiltonian cycle, then we've got only a smaller number of cycles in G prime. So let's do the calculations involved, and then we'll see what we need to do. So if G has a Hamiltonian cycle, then G prime has at least, let's get a lower bound for the number of cycles in G. So the Hamiltonian cycle is a cycle that contains n vertices, and there are, that's in G. So there are n steps between them. When we transform that to a cycle in G prime, each of those steps between them will get expanded to an n plus 1, 2, 3, 4, 5. So to n plus 1 steps of this form, and for each such n plus 1 steps, there are 2 to the n ways of making them. So we've got n different transitions in G, for each of which we have 2 to the n paths in G prime. So in total, there are 2 to the power of n, all to the power of n paths, at least cycles in G. So at least 2 to the power of m to the power of n, which equals 2 to the n squared ceiling to the log to the base 2 of n. These paths, sorry, not paths, cycles. In G prime. Well, sorry, I've already said G. I should say, actually, each of these cycles is going to have length n times n plus a bit, n times brackets n plus 1 or something like that. And because I'm just counting cycles as sequences, that gives us an extra n times n factor here that we could multiply this by. But this bound is going to be enough anyway. We're looking for lower bound, and this is enough. So this is the reason it's going to work, whichever way we count the cycles. So if G doesn't have a Hamiltonian cycle, then what can we say? Let's go back here. If G doesn't have a Hamiltonian cycle, and what we know is that the longest cycle in G is of length at most n minus 1. But then all cycles in G are of length at most n minus 1. Now, every cycle is a sequence of vertices, and there are n possible vertices to put at any place in the sequence. Using that, a little bit of an argument on top, we can show that there, or one can observe, there are, moreover, at most n to the power of n minus 1 cycles in total. So you can think about that. I mean, every cycle is represented by a sequence of vertices. It needn't have length n-1 because it might be a shorter cycle, but nonetheless, a little argument, it's not difficult, and I'll let you think about it, can show that there are at most n to the power of n-1 cycles. So therefore, the number of cycles an upper bound, or the number of cycles in G prime is, well, n to the power of n-1 for the number of cycles in G, and then each cycle in G can contribute, well, will contribute a lot of cycles in G prime, but once again, we're multiplying, each cycle is going to contribute, in G is going to contribute 2 to the m cycle, 2 to the n to the power of the length of the cycle in G prime. And since all the cycles are at most length n-1, we get 2 to the n to the n-1. So that's an upper bound. So this is the total number of cycles in G, and for each cycle in G, because it's at length n-1, it gives rise to at most this many cycles in G prime. So when we work this out, we get that this is, well, n to the n-1 times 2 to the n times n-1 times the ceiling of log n. We can take 2, well, 2 to the log to the base 2 of n is of course n, but here we've got the ceiling in, but 2 to the ceiling of log to the base 2 of n, let's write n over bar for it. So this is n to the n-1 of n over bar to the n-1, where n over bar is defined to be 2 to the ceiling of log of n. That's simply the smallest power of 2 that's greater than equal to the number n. That number, n over bar. And this is less than equal to, well, n over bar is greater than or equal to n. So this is greater than, so this is less than equal to n to the n-1 times n to the n times n-1. So that's n to the n-1 plus n n-1. So this is going to work out. So this is n squared minus n plus n minus, yeah, which is, so that's equal to n to the n squared minus 1, and that's strictly less than ceiling n to the n squared, which is again 2 to the n squared up to the base 2 of n. Okay. So what we can see is that if G has a Hamiltonian cycle, then there are at least 2 to the n squared ceiling of log to the base 2 of n cycles in G prime. And if G doesn't have a Hamiltonian cycle, there are strictly fewer than that number of cycles in G prime. So the decision procedure, So the decision procedure for Ham, or a directed Hamiltonian cycle, is compute the number of cycles in G prime. If this is greater than or equal to 2 to the n squared ceiling of log to the base 2 of n, except, and if it's strictly less than 2 to the n squared log to the base 2 ceiling of log to the base 2 of n, reject. And we do. Okay. And what that argument shows us is that, well, we see, it shows us essentially how counting can give us more information than counting is harder than deciding, because it gives us sufficient additional information that we can use it to solve harder combinatorial problems. Good, so that's one example of a problem that we can decide easily, but we don't know if we can count the, well, it seems unlikely that we can efficiently count the number of solutions. So when I was suggesting what we might prove about it, one of you suggested that we might try to prove that if we can compute this efficiently in polynomial time, then sharp p equals fp. Now that was a good suggestion. It doesn't hold, as far as I know, for this problem, but it would hold if we had shown this problem is complete for the class sharp p. So we've got an interesting class sharp p, and the next thing I want to do is introduce the notion of complete problems for this class. And we're going to see that there is actually a problem that's efficient to compute, that's efficient to decide, but whose counting problem is not just hard, but is indeed sharp p complete. So if that problem were polynomial time computable, then all sharp p problems would be computable. So let's So a function f is sharp p complete. You can probably guess what the definition is to a degree. If it satisfies two properties, f belongs to sharp p, and secondly, f is sharp p hard. And you can also guess that by now that sharp p hard means that if we have any sharp p problem, that we can essentially, in some sense, reduce solving the sharp p problem to solving f. Sorry, yeah, so we can reduce any sharp p problem to solving f. But actually formalizing what that means is going to take a slightly different form from how we've done things in the past. We're now talking about, we want to talk about when we can, given one function, so we're going to talk about f being sharp p hard, we want to talk about when we can compute another function, when we can reduce a function to f. So it's not a language reduction anymore, it's reducing one function to another. There are actually different ways of doing this, And I don't want to be systematic and talk about them all because that would take a lot of time. So I'm just going to introduce the notion that's used for sharply completeness because this is also an interesting notion. And it uses what's called oracle Turing machines. So we say there's a slightly more formal definition in the notes. I don't want to spend time on the formal definition now. So, a Turing machine with oracle or a function f from sigma star. The idea, so to actually formalize it, you need to talk about a slightly modified notion of transition function for the Turing machine. But I don't want to go into it in formality. I just want to give you the idea is that the Turing machine can compute in the normal way, makes its usual steps, but it has a special kind of step it can make, which is that another thing it can do is at any point during its execution, it can say, I want to compute a value of f. And it's got an oracle. There is the famous oracle at Delphi in ancient Greek times, which would answer any question you wanted to ask it at some cost to your soul or something. I don't quite remember. But here the oracle is a function that we rely, it's an oracle given to the Turing machine. The Turing machine is allowed to, at any point in its computation, ask its oracle, okay, what is the value of f on 53 or something like that? So what is the value of f on some input string? So it computes as an ordinary Turing machine, but at any point that has the possibility of performing an additional computation step, an additional computation step ask the oracle what is f applied to what is the value of f applied to the string on a special, the current string on the oracle tape. So we have a special tape called the oracle tape. And on that oracle tape, anything can be written on it at any point. I mean, the Turing machine plays with that tape as usual, but at a certain point, the Turing machine can say, it can ask the oracle, okay, look at my current value on the oracle tape. What is the value of the function f applied to that? And the oracle writes that answer back on the oracle tape. The oracle writes the oracle tape. Another way of thinking of it, so as I say, make this formal by modifying the transition function. That's done in the lecture notes. Another way of thinking of it is that the Turing machine has access to a black box, as we like to say, it doesn't see the insides, but it can feed at any point, it can feed an input word into the black box, and the black box computes f and then feeds an output word back to the oracle Turing machine. And the point is, we don't count the time taken by the black box as part of the computation time. This is just one step of computation from the point of view of the Turing machine. And this is one step. mean by FP hard here sharp P hard, so F is sharp P hard. So what we want to say is that any sharp P function G is reducible to F. But the notion of computing with an oracle gives us a nice notion of reducibility. The obvious thing to say here is if we've got a sharp P function G, we can compute it in polynomial time by an oracle Turing machine that has an oracle for F. Okay? So that's a natural way of reducing the problem. We say, if we could compute F, if we had a black box that could compute F, then we can compute any sharp P problem G. Okay? So if for every G sharp P holds that G is polynomial time computable by a Turing machine with an oracle graph. Okay. The notation for this, so G is in class P, so FP, because it's computable, it's computable in function polynomial time. FP, we put a little exponent here, F, and this means a functional, a Turing machine that computes a function in polynomial time with an oracle for the function F. Now, in spite of me leaving this whiteboard up here to use later, I've snookered myself, which is, so snooker is a game like billiards or a bit like pool in Britain, but snookering yourself means putting yourself into a situation that's hard to get out of. I've done the wrong thing because I wanted this board to be visible at the same time as this board, which I'm now going to write on this board. So I should have put this up there, but never mind, you just need to remember this. I'm going to bring this board down. So I want to define the class FP to an oracle. Well, that's going to be the complexity class FP to the G, which is function polynomial polytime with an oracle for G. But all those functions that are computable in polynomial time, we've got a black box, an instant response black box that computes a function G. And basically the definition is exactly as before. So it is just if there exists a deterministic Turing machine and that computes F and there exists a polynomial P such that the time is bounded by the polynomial, except that we add the condition here, deterministic Tn and with an oracle for G. Put that back up now. And let me just state theorem that counting problem satisfying assignments, probably unsurprisingly, is sharply complete. So that does mean, although I haven't proved this, but that does mean if we could solve the counting problem for satisfiability in sharp p time, sorry, in polynomial time, then sharp p would coincide with fp. That follows from that. But the point is that we're used to problems like satisfiability being complete classes, and that also extends to counting. And I'm running out of time, or I've basically run out of time. I said I might extend a bit, but I don't see any reason to extend. I don't really want to say that the notes have a little bit more about the proofs than I'm going to say now, but essentially, the proof is essentially the Cook-Levin argument, the Levin argument. Now that might sound strange because there's nothing in the Cook-Levin argument about Oracle Turing machines. But nonetheless, you go through the Cook-Levin argument, and the crucial thing about the Cook-Levin argument is that it preserves the number. If you've got so it reduces any NP problem to satisfiability problem, and in doing so, it preserves the number of certificates. So you get it does so in such a way that the number of certificates for the original problem are the same as the number of satisfying assignments for the formula that it's reduced to. Actually, the way I presented the Cook-Levin argument, it was rather about non-deterministic Turing machines rather than the certificate definition of NP. But in that context, what happens is that the number of satisfying assignments for the formula that you reduce an NP problem to is the same as the number of non-deterministic runs in the non-deterministic Turing machine that solves the original problem. So those kind of considerations come into this, making a formal proof out of this, but it's essentially the mathematics behind the argument is essentially the same, and essentially that argument shows that. It's a very powerful argument. There's similar reductions have worked for showing that satisfiability is NP complete, showing that true quantified Boolean formulae are p-space complete, and now that sharp sat is sharp p complete. A similar argument works. Okay, so I think that's enough for the lecture material for today. It's 10:05. I'm going to stop the recording now. We'll have a 10-minute break, and then if you do have, and then it's like a sort of open session. If anybody has questions about the homework, then I'm happy to discuss any issues at all. Also, like what level of detail you should go into in this sort of thing, or anything you want about the homework. But we'll have a 10-minute break first till 15:15. So let me stop the recording because I'm ending the recording now.